And with Hugh having opened the event with his foreword, I will be the one to introduce the first speaker. Although being Czech by origin, Tomáš Černý is now doing his research in the US. He is a professor of computer science at Baylor University, and we're quite happy to have him here and to cooperate with him, as Tomáš, even now in the US, has kept lively relationships with Czech universities in Brno and Prague, his alma mater, and Red Hat as well. So ladies and gentlemen, Tomáš Černý.
So thank you, Martin, for the introduction, and today I'm going to talk not about that, but about that. So let's try to connect it with the remote screen. And I can see both of the slides properly in here. Oh, here we go. Thank you so much. So today I'm going to talk about, first of all, thank you for having me. It's always a pleasure to go to Brno and enjoy to be around people that have really fantastic community. So I always love to come back. And I will present you some research that we have been doing in the past few years, and it also involved here the Red Hat in Brno. So Martin already introduced me a little bit. So I came from university that also starts with B, so it's very close to Brno, right? However, kind of nice thing about it is that there is a very large Czech community coming from Moravia. So they make there the Moravian kolaches and so on. So anytime you go by, you think about it. And their local stores have traditional Czech kolaches with sausage and jalapeno. So I'm sure that you really enjoy that. So the research I do is related to cloud-native systems and static analysis. And just recently I took 35 students from the US, but some of them were also international, with me to do research here in Red Hat in Brno, and it was a fantastic experience for the students, and they always come back, and it's a thing that they will never forget. So just to outline some of the research that we have been doing was recently awarded by many conferences, and I'm very proud of that because most of this work is done by students. So just recently we went to Microservices 2022 and we just got 2 awards right after each other, and another conference. It's like finding mushrooms in a forest. I am really happy about it. I never thought that we could do that. And again, this is with the help of Red Hat. So what I'm going to talk about today will be kind of easy topic on what can we do in order to improve development of microservices and especially their maintenance and evolution. And what you probably like to do as developers is to have your Eclipse or IntelliJ or whatever you use to tell you that there is something wrong, to get a quick feedback. Unfortunately, since microservice systems are decentralized, you don't know if some changes that you do in your local repository would actually impact the remote repository. This is some sort of challenge that we would like to look into and see whether static analysis could help us with that. So I will start with a question to engage with the audience, right? And anyone could just tell me what is this graph, what could it represent, and how do we get that? And it's absolutely fine to just shout at me what it is and which tool did present this, or which tool is able to derive this from microservice system. Yeah, it's some kind of communication graph, right? So maybe you have been using Jaeger, or maybe you have been using Kiali and something like that. So when you deploy your microservices and they are interacting with the end users, or maybe when they are interacting with your dynamic tests, they let us know that they are there, that they are communicating with each other. And we typically do this in order to understand how the decentralized systems communicates as the whole thing, so that we could identify some optimization opportunities, maybe some issues and bottlenecks and so on. Well, there are some issues with this because, as I mentioned, we typically do that when it's deployed. And that not might be something that is way too friendly to developers, right? So first, why do we do that? To understand how the system looks like, what are the dependencies, and if there is some kind of ripple effect, what could it be? So let me give you an example. You would deploy a new microservice version. It will introduce a cyclic dependency, and in a few minutes you take down AWS. Actually, some colleagues that I'm working with have done that, and they actually took some of the cloud centers of the AWS because they had an unfortunate cyclic dependency, and you could imagine the bill as well. It's very high. So we would like to prevent situation like that, but that's not only the cyclic dependency that could cause an issue, right? So what is the major issue? Most of the code that we have is decentralized. The systems, when we deploy them, they are decentralized, and when you could see that it's a separate code base, it's typically self-contained. So you don't share much of the code between different microservices. And that is an issue because it introduces completely different mindset than what we are used to when we are learning about building systems that are monoliths. No. So let's do it the old way. It doesn't work the old way either. Okay, so I would probably need someone who is, oh, here we go. Now we can have it, and it goes way too fast. So how do we do it these days when we do what is available on the market? We would employ the deployment to the cloud, we would involve the customer to play with the system, and then we would use DevOps to actually give us the statistics. So what could we do would be open telemetry. We could also introduce API gateway that would put into every request a unified ID, and then we would be tracing through centralized logging how a particular transaction spans across different microservices. And based on that, we would be able to reconstruct this kind of graph. However, it has many challenges. First of all, I need traffic, and where is the guarantee that the traffic that I will have will cover the entire system? Maybe some parts of the system are not currently used, so I will not be able to reconstruct this graph completely, right? There is certainly a delay from when the developer introduces a change and when it gets to the production and when the customer is about to access it, or maybe when the tests, the dynamic tests will be performing it. So there is no direct feedback to the developer. They might get a feedback within a few days, and it might be too late. Static analysis would certainly take care of this, right? So we are trying to see if static analysis would be able to address this. We wouldn't need any traffic, we wouldn't need any DevOps. We would get an immediate feedback on any kind of code change analysis or code change impact. But there are many challenges that we have to face. So first of all, we have decentralized systems. There might be language heterogeneity, and then how do we connect these things together? And I'm going to talk about this throughout the process, and then I will show you what we actually accomplished by doing that, what kind of proof of concept we have. So let me start with the thing that conventional static analysis and microservices don't like each other because they are completely different culture. Typically with static analysis, we do low-level code analysis. It's limited to single code base, pretty much what is implied from what I have said so far, and it's language specific, so it's like monolingual. But with microservices, we go for decentralization. So we have to deal with that. Highly likely microservices are not written in low-level language, and those parts, there are multiple microservices, could eventually be heterogeneous. It might still be Java, but here is Java 1, here is Java 2, here is Java 3, and the versions will be independent of each other eventually. But it's also very common to have Java, Python, C++, and other components talking to each other. So what do we observe when we look into a code of a microservice? We observe that they are not really using low-level code, but they are building on components. And I would say nowadays, if someone is building a microservice without components, why would you do that? Because the components are pretty much making it much simpler. And this is not something that is just an option, but this is best practice. And we should typically follow a best practice, right? So on the top, we can see a controller. On the bottom, there are some data entities that are probably persisted, or we operate with them, we send them somewhere through a data stream. And in the middle, there will be some service. So where is the issue and where I'm going with that? Our code analysis should identify that there are components. However, that might be one of the challenges, and that's one of the challenges that we are looking into. So we need to recognize those components, and we would like to, of course, understand how can we utilize, once we have those components recognized, any kind of composition of the decentralized code bases, so that we have the holistic picture of the entire system, not even running it. And we have to face another issue that the code base is heterogeneous. So of course, we will need some intermediate representation of whatever we reconstruct from the code. And our sort of idea is to utilize the components that we can extract from the repositories for the microservices, because that's what the developers are using to build the microservices. So here a little bit of visualization. We have there a couple of repositories that might be decentralized. Of course, it could be one repository, absolutely okay, but then you are violating the 12-factor app, which is a standard by Heroku when it says that it should be decentralized. We would extract information from each of those repositories, and then we would like to somehow combine it. And I'm going to give you more details as I'm moving forward. So first of all, is there any good intermediate representation that we could use? Yeah, well, there is well-recognized low-level virtual machine that we could probably use for this purpose. It deals with heterogeneities, but it's on the compiler level. So we don't really use it in order to identify, hey, here is component A, here is component B, here is component C, but we use it in order to operate with it. So it's not a perfect fit for whatever we need, and when we look for the alternatives that are known. So we have addressed this, and it was not that hard to actually develop a unified abstract syntax tree that is language agnostic. You could see it as a superset of all languages, however, it's not always the case. Sometimes you have to do some manipulation with the code in order to add it to the tree. An example could be there are some operators in Go that do not exist anywhere else, or you could see a switch that you will actually convert into ifs when you are representing it through the tree. But you know, this is not the issue. This could be seen as some auxiliary intermediate representation. The thing that is more challenging is to detect the components out of it. But it already prepares our path in order to detect the components, because this is a tree and it's very easy to traverse a tree. This is something that everyone have learned in their undergrads, right? So we can see a tree that we will be traversing, and then we introduce detectors that are applied on this tree, and they're traversing it down and trying to find some properties that there should occur in order to say, hey, this is a component. And of course, if we have abstract syntax tree, then this mechanism of those detectors can apply across different languages. So it is not anymore language specific. Of course, in order to build the language agnostic tree, we need a language specific parser. But once we have the intermediate representation of the language agnostic tree, we can reuse those sort of detectors across different languages and then get a unified representation that contains those components. So here is an example. I have a very small code snippet. I turn it into an abstract syntax tree. Here we really don't see that it's language agnostic, but it will look most of the same. And we identify, let's say, a pattern that we would like to appear and some sub-patterns. So when we are detecting components, it could be as easy as, is there an annotation, but not everyone is Java, right? So in C++, we might be actually checking, does it inherit something? Does it have this method? Does it have another method? So it is not a single pattern. It could be a really multiple patterns that have to appear within the tree. So we might have a match here of the first pattern, and for the second pattern, we might have a match here. And we say, okay, we seem to identify the component, and then we would like to extract some meta information about that component, and that's where we have the callback. And here we have it just a primitive to write it down. But we could be extracting it into some context that we would be using in order to process it. Okay, theoretically it sounds fine, right? So we need to assess it. So we took two existing benchmarks. One that is coming from the International Conference on Software Engineering. The other one comes from APLOS, and these are the top conferences. So Train Ticket and that Star Bench, which are One of them is in C++, one of them is in Java, benchmarks that we are using and most of the community is using to assess whatever contributions there are. And we were able to detect components with very high precision and pretty good recall. We already have this number slightly bigger, but this is what we have presented in the paper. Pretty much the downgrade of that was that this benchmark uses aliases for endpoints, and we didn't expect that there could be an endpoint that have two paths to get there. Now we are able to get it very high. So it seems like this is a way to go, since two major mainstream benchmarks give us those numbers, right? But now there is another issue we have to overcome. So the other issue is, how do we connect the code bases? So let's assume that this is a microservice A and this is a microservice B. We need some ingredients. How to connect those microservices in order to understand how they are dependent. One thing that we can apply is the inter-service communication. So here is maybe an endpoint and we need to detect that this component is making an endpoint call. It might be REST call. Of course, there might be also communication on messaging. What else? Very often there is bounded context. That means that there is an entity that is appearing twice, maybe with some addition attributes across the microservices, so we can fuse them together. And what is often also very useful is that there are deployment descriptors, because most of the things you will do will go to some Docker, and this Docker is part of a code base. So it's not really just a static analysis by looking to the code, but looking to the entire code base in order to be holistic. Okay, so if I summarize this, we assess each code part that might be heterogeneous. We get lost. It's our first step. Then we detect the components and we extract some intermediate representation that is using components and component calls. And then we can determine the holistic perspective, so connect the system intermediate representation into one. So such as if we fused the decentralized systems into a virtual monolith. And then we can operate with it, right? But now your question is, so why did you do this? So let me show you some examples why would we do that, because it opens a Pandora box with opportunities. So some of these are software architecture reconstruction that is especially useful when we need to understand the system, visualization, reasoning about the system, so the human-centered perspective, the technical perspective, where we have some automation, right? Maybe detecting bad smells. No one likes bad smells, right? Maybe it's a funny term, you haven't heard it, but it's like anti-pattern, or maybe some poor metric. And some maybe reasoning about code clones. So here is the first paper we did when utilizing this perspective, and it's related to software architecture reconstruction. There was a fantastic paper by Florian Rademacher, I believe from Austria, maybe from Germany, I'm sorry if I'm wrong, and he did it manually. So pretty much he would look to the code base, he would look to the documentation, then he would be constructing every individual part, he would be fusing it together, and then he would be reasoning. And typically there are multiple views that are being done. And we have automated this. So pretty much we just feed it with the code base or with multiple code bases, and we are able to extract all the views that are typically an outcome of this process. So that was promising, and of course we wanted to see how can we visualize it, and those are two examples how we would use conventional visualization techniques. And you know, microservice systems are big. They are really big, and it seems like UML is not really the way to go, because there can be many components. Well, maybe if you look very well, there are some of the red highlights, and these are the inconsistencies that our system didn't find from the manual perspective. And of course, there is always space for improvement. However, what I'm trying to say here is that for those large systems, conventional approach uses two-dimensional visualization, two-dimensional space, and maybe this is not the right fit. So maybe we should look for something else, something for more engaging, more interactive. So here is some more interactive approach that one of my students did to actually use augmented reality and visualize the system in 3D perspective. And we were using some of you to actually test it in our user study. Don't worry, it was IRB approved. And We have identified some of the good things and some of the bad things, right? So for instance, it's very hard to use a cell phone and walk around your room to find the endpoint or the component that you need. On the other hand, it is cool that you can actually interact with it. It's not like plain model, but you will highly likely need some web app that does it, and especially you need to search. So here is the next thing that we have tried to use. So we looked into some JavaScript-based graph visualization, and pretty much we are using this now because we can have it as a web app, and we can very easily search with it. So here I have 2 examples, and I believe that this is something from Red Hat. This is the pipeline that our collaborator Pavel Tišnovský is using, that we are visualizing. And of course, one of them is 2D, one of them is 3D. So right now, I have a bunch of students that are playing with it, and we are trying to also track the rotation so that we could go back in a history and see what was the previous view. In order to operate with it. And now we are trying to add there more details. So whenever you click, let's say, on some button, on some bullet, it will tell you more details about the system. And you could zoom in. So we really are going for more interactive approach. And imagine that you have a developer, you are working on this particular thing, but you would like to see if I make a change, how we can promote. So this is mostly focused on the human-centered perspective, not on the automated reasoning that would be the technical perspective that tells you, hey, here is something wrong. But now another paper that we looked into, and I had a collaborator, I think Vašek Mateáš is here somewhere hiding. So we were looking into access policy consistency checks. This is specific to Java because Java on the top of endpoints is using annotation who can do that, right? And it's absolutely fine when you have your code base, you can analyze it. But now if you have multiple code bases, you are wondering, wow, so what if there is some inconsistency? And we can do it, right? So here is one microservice, here is another microservice. We can extract the call graphs, and we can also detect that here is an explicit endpoint call within. So we can actually establish one sort of virtual application that connects this path into that. Now we can be analyzing whether the resources we are accessing to from different locations, from here or maybe directly from here, are actually using the same role-based access control, same security measure. What we have identified are 5 patterns that, of course, it's easy to find out that, hey, some of the endpoints are enforcing something and some others accessing the same data are not enforcing it. Maybe there might be an easy typo to find. There might be entity access violations, such as from different locations you access to the database once you need admin and once you need a regular user. Problems with hierarchies, problems with unrelated access violations. So this could at least give some hints to the developer, hey, there is something wrong when we fuse these systems together. And you know, if you look at the train ticket, it has 40 microservices. But it's not a problem to have hundreds of microservices. So it cannot be a human task. It's way too complicated. Another really cool thing, bad smells. How many of you ever heard a bad smell? I want to see your hand. Well, not many, right? How many of you heard anti-pattern? More. That's pretty much the same thing. Bad smell is, let's say, a super category of it. And Davide Taibi from Finland wrote a very nice paper on definition of microservice bad smells. Well, we took what we have and we analyzed all of the 11 bad smells automatically. That's great, right? So we didn't need to analyze it manually. Right now I'm working with Dr. Taibi on identifying microservice bad smells, and we already identified 137. That's a very high number, right? We don't know to detect them yet, but it at least aligns the path for our future work. Another cool thing, detection of semantic clones. And what is a semantic clone? Well, you know syntactic clone. You copy-paste something, right? And they tell you shouldn't do it. And that's good advice, because no one wants to have a replication. And the problem is that you might end up with a similar bad situation even when you don't do that. Simply system integration. One company bought another company, or maybe we are integrating some system that was developed originally for something else. And now, after a long time, we identify, well, those two things are doing the same thing, but they look completely different. And now take into account that one of the systems is in Java, the other system is in C++. And you are like, okay, now I know it, now I have to fix it, but before you know it, it's there, and it's a bad smell. It shouldn't be there, because it might introduce issues later on. It leads into a technical debt. So identification of it would be useful, and we are not doing the syntactic clones that look the same, but we do the semantic clones that do the same thing and look different. So in this perspective, we can extract the graphs, and since the graphs are sort of intermediate representation, we can compare the graphs. How we do that? Well, we will do pretty much what I have described so far, turn the source code into a graph, and then we quantify and compare particular components that appear within that graph. So for instance, are these the same controllers? Are they doing the same thing? Are they operating with the same data? Well, if we don't know it and we use just the conventional techniques that are operating in low-level code, we will be iterating through a huge set of opportunities for code clone. But here we can very easily eliminate what is clearly not a code clone because it is operating with different data, right? So we moved the problem slightly more up, and we turn it into analyzing the components. So we know where is the call graph, right? So I go through controller, I go to service, here is some REST call, here is maybe some repository storage and so on, and it stores a specific data. So I can compare those graphs, and it's very easy to avoid situation when I compare controller to repository. I will always compare controller, and then look whether the paths are the same. And that will lead us into identification of some similarities. And again, we used a train ticket in order to identify it. And we identified some that had pretty high indication of semantic clones. So to wrap up, because I have a couple of last seconds, what did we demonstrate? Well, we demonstrated that there is a space to fit in static analysis into decentralized systems, right? We showed that our experiments could be a good use in order to develop some tool in practice that could reasonably help developers, and most likely there are a lot of developers of microservices. Still, we just argue. We don't say that necessarily this is the right way to do, but we demonstrated a couple of examples that are pretty solid on suggesting that these things that are being done manually or with dynamic analysis could be done with static analysis. Future work, architectural degradation. So we could look how it changes throughout the time. So you analyze GitHub, right? So here you had the original idea, how it changes throughout the time. And maybe you could be preventing developers to do things that they shouldn't be doing. Space for improving the component detection and so on. Messaging integration, we have a work in progress. Integration with dynamic analysis, there is fantastic opportunity for research here. And that's how I connected with some colleagues from Finland that are doing it. Another very interesting thing is that we could use this structure in order to always reassess the microservices, whether they are properly shaped for the task that they are doing. And we have tried to do this on slightly different perspective, turning monolith system into a cloud-native system. We have used soft k-means. And apparently the community very much liked it. So right now we are looking whether we could continuously be checking the microservices, whether they fit the task that they were meant for, because time changes and they evolve, and the customers evolve as well. Thank you so much. I apologize for 1 minute 37 seconds extra over time, but it still is within the range that I have for questions. So could I have Martin here to help me see the audience questions?
Applaud the speaker. Before we dive back into the questions, I just wanted to remind you that apart from posing new questions, you can like existing questions and thus influence which questions will be asked. So starting with the first one, what do you specifically mean when you say the term component in the context of the microservices analysis?
So I would go with the Java terminology, anything that you annotate, which originally was an object and now it has annotation and it can be recognized by container as a specific thing, such as controller, service, repository. It could also be entity. However, it is more complex. So we like to recognize high-level structures. So even a REST point end call is a high-level block that we would like to operate with, or when we are connecting into an endpoint. So all these things fit within what we want to recognize in the component graph, however, mainly driven by whatever you recognize in Java. And if you look at C++, they have the same thing. When you look at Python, they have the same thing. When you look at Go, you still will recognize controllers, something that has to be persisted and so on. I hope it answered the question. If not, you can catch me later and we can go into detail.
The next question expresses appreciation for the 3D views, but asks whether you have examples of insights that pops out in the 3D, but are not really applicable in the 2D or cannot be seen that easily.
Yeah, so we are currently conducting a study on that. So our initial perspective was, is this even a good fit? So now, of course, there are plenty of questions that we are raising, and that's the full research that I have with my student group. So I don't have an answer for that. Of course, we want to assess the directions to look into.
One more. Is your solution applicable to AWS serverless application model? Are there any major differences regarding this?
Yeah, so that's a great question. Serverless is certainly growing in popularity. However, there is a significant difference because in serverless, you simply go for functions. So you don't necessarily need to consider that you would always have the full graph coming from an endpoint down to some storage. We did not specifically look into that because the application itself highly likely will not be solely serverless. Implementation. It would typically be a microservice that decomposes the system, and the serverless would be, let's say, for some kind of functionality where I need to convert a picture before I store it or do something like that. So there is certainly space for improvement. We didn't assess this. It is on our radar. However, we have fewer workers than opportunities there are for research.
Yeah, understood. Generally, thanks for the answers. There are other questions, and I believe people will approach you during the break. You're definitely encouraged to do so, and you see Tomáš actually wants it. As there's no further time, I'd ask the audience to thank you one more time.
Thank you for having me.